Okay, first thing I want to go over is Hopper V1. So Hopper V1 was the first TVC vehicle I ever made. So it was very rough. Uh, it was in development from last August, and then it flew December 2nd. So pretty long development time, mainly because of the software and just some other uh, crazy issues that I encountered because this was my first rocket. So let's take a look at this flight. So, first thing I want to go over here is the this pipe here. This is the water deluge system. It's pretty unnoticeable through this camera angle, um, but for other future launches, it's more obvious that it's there. Um, it's completely unnecessary for the model scale here, but I just think it looks really cool. So it also helps evacuate a lot of the motor deposits that it leaves. So you could kind of see it. I don't know. It's definitely not obvious to see here, but you could kind of see some sprinkling action going on, and then the motor lights, and then you could barely tell it exists, but it's there. I activated the pump a little bit too late. Um, so yeah, that's the water system. So we have ignition here, and a lot of the motor deposit went back up and into the TVC mount here at the bottom. I don't know if that caused any issues, but it's definitely a point of concern for future launches. Yeah, when we have liftoff here, you could instantly tell that the rocket has pitched over to the right, so that's on the y-axis. Um, Pretty much instantly. I don't think it went up straight for any amount of time. So now we're going to switch here to the uh, tracking camera. Pretty much tell the rocket is probably at a 45-degree angle here, maybe a bit more. Got some sparks shooting out here. Uh, don't really know why or what those were from, but they were there. You could definitely see the motor mount is definitely not correcting there, and I'll get to that a little bit later. So yeah, it instantly, this happens in a matter of seconds. Is In the slow motion, it happens way slower, but in real life, this is like pretty much instantly. In how fast it just immediately decided to flip over here. Yeah, so we get to this part in the flight. You can kind of see the motor mount is at a bit of a different angle. Trying to fix it a little bit, um, but you could clearly see that that's pretty much irreversible. And then we hit into the ground here. You could even tell this is probably a bit more obvious that the motor mount is at a different angle than the rocket is. Yep, and we hit the ground here. And a big thing with this rocket is it really had no structure on the inside. It was very bad at dissipating a lot of impact load. Um, So what happened was the computer or the flight computer got like crunched in a little bit, and I had to cut open the tube to get the computer out. It was just very, everything was damaged after this impact because I mean it was a pretty hard impact. Um, Reviews. This was on the base of the launch tower, looking up. I don't really know what I thought I'd get from this. I thought it was just gonna be pretty cool, but you can definitely see the rocket a bit more clearly here. It is definitely not vertical. Um, yeah, you can kind of see this is the y-axis servo housing here. And yeah, there's the motor. And that's pretty much it for this camera view here that I had. You can see there's pretty much little to no correction coming from the motor mount there. This is onboard camera for the rocket. It's pretty blurry. You can't really tell what's going on just because the rocket flips out, really fast. This is in real time, so it's gonna go pretty quickly. Yeah, so like in no time, I think it was like was that like 1.5 seconds ish um, that it took for it to go from the pad to hitting the ground. This is in. I slowed this one down in the editor. Um, but yeah, you can't really tell what's going on just because how fast it's going. But yeah, that's was Hopper V1's flight. Okay, so Hopper V2 um, was an interesting rocket. So it only took a month to put together, compared to Hopper V1's like 4 or 5 months to get launching. V2 only took a month to from design to production and launch. It had a different TVC mount. It had uh, I would guess it has a better internal structure, so it has carbon fiber rods. Um, a lot of I definitely beefed up the structure inside of Hopper V2. It also had a parachute deployment system, so that's what Hopper V1 lacked. So I was expecting if V1 worked, which it didn't, um, it would just come down and kind of destroy itself. So I wasn't expecting V1 to, you know, I wasn't expecting to recover it in a reflyable state. V2, I built it like a tank, so I knew that if the parachute system failed, um, it would be okay. So the parachute system was basically a glorified slingshot. So it had 6 rubber bands at the top, and I'll go over this later when I uh, go over the 3D model of Hopper V2. But it has 6 rubber bands at the top, and it's basically just spring loaded. Rubber bands have this weird thing where their elasticity varies with like it's really variable and it's never really constant. So the parachute system only worked once, but I only flew Hopper V2 twice, so I'll never really know like if it was actually gonna work. But I'm never really doing that again because of just how like it just was not reliable enough. Um, Another thing wanted to change with Hopper V2 was its center of mass. The Hopper V1, its weight was very distributed along the rocket, and it's very somewhat top heavy, somewhat not. Hopper V2 was definitely bottom heavy, and the center of mass was really low. I kept everything really low uh, to towards the bottom of the rocket. So let's take a look at Hopper V2's CAD model. Sorry for the lower quality here. The My laptop with Fusion 360 on it was being a bit buggy with the microphone, so I had to improvise here, but it's the same thing. So this is Hopper V2 here. So starting off at the bottom, well, we have the motor mount here. So you kind of see how I compacted it all in here. So the Y servo would go here, and the X servo um, would go in this little section here. So if you go underneath, it's a flat bottom motor mount. So there's nothing sticking out, and it's nice and even, which makes it easy to center, but hard to fit into the tube. And that's why I had to make this TVC can to like specifically fit this motor mount. This here is the pad attachment system. So this is what attaches the rocket to the pad. It was a bit flimsy, um, but it worked for what it was. So going up, here we have the nose cone here with its stoppers, which kind of kept it on. And then this guy here is the rubber band crown. So this is what all the rubber bands went into to hold onto the parachute ejection plate, which I'm going to hide the airframe. Okay. So now in here, we have the parachute ejection plate here. So how this works is there's a servo on the outside of the airframe with a steel rod that goes into here, and that basically holds this plate in place. So the rubber bands get linked here, and they go all the way up to the crown at the top. So it holds them in tension, and when the rocket aborts or tells the servo to pull back, it will pull back and release this, and the rubber bands will fling the parachute out, and these two rods bump off the nose cone, so the parachute doesn't have to do that. And it was a pretty good system. It just didn't really work reliably 100% of the time. So it was very annoying to get working. Like I said before, it only worked 1 out of 2 attempts, so I'll never really know, how reliable this thing actually was. So running down most of the way down the rocket are carbon fiber rods, but the carbon fiber rod is covered by this piece here. Uh, if I hide this, you can see the carbon fiber rod there, um, that runs down. So these guys here basically are spacers, so they space out the ring or the different rings. So this was area here was just empty space, and then this area was the battery compartment. And in here, I don't have it modeled in, but the flight computer would be sitting in here. You can kind of see the slots for the breadboards. I'll probably have a picture of it on on screen with the computer in it. But yeah, it was a pretty beefy unit, which made this rocket pretty heavy. I had also a shield. This guy here is a shield from the motor if anything happened. Um, but I mean, yeah, that's really Hopper V2 and its internal structure. It was definitely a interesting rocket to design and build. But I mean, yeah, I mean, all of this stuff just made it really heavy. And when I go over Hopper Gen 3's airframe, you will definitely see, or sorry, not airframe, it's internal design. You'll definitely notice a difference in the design, and then also that equates to the big difference in weight. So yeah, this is Hopper V2's CAD model. This is Hopper V2's inaugural launch. It flew twice. This was the first one. So some things you can notice here is that the battery for the motor mount was it came out the side of the rocket. Up here is the counterweight. It was pretty much just a bunch of quarters taped to the side of the rocket. And that was to counteract the weight of the mechanism of the parachute system. So it made it kind of top heavy ish, but mainly the center of mass was like down here a little bit. Here we have the motor mount can, which made the rocket really heavy. Um, so with some of these flights, you could tell, and I know some people have been commenting about this, how the motor is underperforming or the rocket's too heavy. The rocket was definitely way too heavy, but I didn't really think it would have a big effect, and I, think it did because the motor really had like little influence on the rocket. But anyway, with this flight, you could definitely see the water deluge doing its thing here. I ran it for definitely way longer than the other one. So here we have ignition, and right at liftoff, you can instantly tell that it's not pitching over really violently. Um, it's still kind of straight up here. You could tell by the plume still hitting the launch table here. Um, pretty centered. I think it's still kind of nicking the outside there, but it's still pretty straight up at this point in flight, where Hopper V1 was already pretty much 45, 50-ish degrees. Yeah, so this was the another camera I added. Just I don't know why I didn't align it with the x-axis. So the x-axis is right to left, and the y-axis is front and back. I don't know why I didn't align it with the x-axis, but uh, I think the next few flights I did better at that, and I aligned it better. But it's just another ground view of ignition and liftoff here. You could see it slowly starts to pitch over um, a little bit to the left and a little bit forward um, as it goes on. And I think that's just primarily due to the rocket's weight just like suppressing the motor's force. Um, so here we have the tracking shot. So yeah, you could definitely see that pitch over more as we get to the end of the burn as the motor is losing its initial thrust spike. Um, so it goes horizontal for a little bit, and I think right here the command was sent to deploy the parachute. It deployed, but this is what I'm talking about with the variability of this parachute system is the parachute was not folded. It was folded too thick, so it expanded inside the airframe, and when the mechanism triggered, the parachute jammed and kept itself in. So it does not come out, but in the data there was a command sent to deploy the parachute, and it definitely did, although I don't really know if it did. Um, but all I know is that the parachute was all the way up at the top, and the rubber bands were um, not tensioned anymore. So that's pretty much a sign of that it triggered. So it does not come down under its intended parachute, and it hits the ground. And it cracked the motor mount can on the bottom. You see that nose cone fly off there. But I mean, overall, this was a really nice flight, and I was really happy with it because it did not flip out instantly. So I think next should be the onboard. So same thing with the last flight. You can't really tell what's going on just 'cause how fast it's going. You can see it hits the ground there. I'm gonna actually skip over the slow motion. This is another cool shot that I kind of threw in there. This is these are the legs of the launch table. This is the water ring here, the shower head ring. So I think pretty soon we should see some. There's the water. So yeah, it floods the plate and it drains out. We should have ignition. There it goes. Yep. So it basically floods out. Sorry for pausing it in the transition there, but it floods out a lot of the deposits. So you can see some of that the soot and deposits from the motor being flushed out by the water. This is real time. So yeah, definitely a really nice flight here. So let's look at the data. Okay, so this is Hopper V2 test flight 1. This is its flight data. I took the time and graphed it. It was really painful because um, I had to hold down the control key and highlight every individual value I wanted um, to be able to make these graphs. I've since then improved how I'm able to the graph the data. Um, but yeah, so it's kind of annoying that I don't have the graphed data for Hopper V1, but it was only 7 values, so I don't really know what I would have gotten out of that. But you could definitely see here there was little no correction on the X here. It was pretty much right from 0 out. Same thing with the Y a little bit, not much there. You could tell here there should be a wave around 0. It's definitely not. Um, this all happens really fast, so you can see if this was still in flight, this would have kept going. Same thing there. The servo positions here, that doesn't really matter. This is the corresponding angle corrections here. So this is the roll. This is the same thing with Hopper V1. I don't think that this is necessarily accurate in what it did, but I would take that with a grain of salt there. So yeah, I mean, it's definitely not what I was hoping for, but it was definitely better than Hopper V1. Um, so let me see what's in this values section. Yeah, so you could see here, this is kind of messy here for just pay attention to this section here. So you could tell this time we got, what's this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 uh, flight points compared to last flight's or Hopper V1's 7. So that isn't much more. I in the code I decreased the delay time, so I decreased it from 100 milliseconds to 45. So that really sped up the code a little bit. and this line highlighted in red is the abort line. So it aborted at on angle X here for at negative 66 degrees. It aborted. So I think the angle was set at negative 65, which is pretty generous. Um, it would have aborted way sooner here if it was set to 45. But yeah, I think that's pretty much all there is. I do not have the angle that it starts at. I don't know if this is angle drift. It could be angle drift. I'm not totally sure. Uh, I'll check that for you guys in a minute, but I don't know if this is pretty much right when it lifts off or this is what, because if this is how the rocket started, this is definitely bad. Um, Same thing with roll. I don't know if this is incredibly accurate. If it is, it's pretty good. Um, 3 degrees per second, which is not right if this is still on the pad at this point. Um, Same thing here. This is definitely in flight, but it's way better than V1s if this roll data is accurate. So this is Hopper Gen 3 V1. So this is the most recent Hopper. So this is the last rocket of this video. So some changes that I made is um, a lot of hardware changes. This is full of hardware changes. Not many software changes, but just a crazy amount of hardware changes. So first off, the rocket shrunk by, I don't have the exact measurement, but this rocket is about the third the size of Hopper V2, so it shrunk quite a bit, which also decreased in mass. I also got rid of the cardboard airframe and I put on or made a 3D printed airframe. So the nose cone, the avionics section, and then the motor mount housing and battery housing down there. So it's all 3D printed, which is really good for um, rapid iteration because for a cardboard tube, if you cut into it too much, it loses its structural integrity. So it's not that great for rapid design change. So with 3D printing, if I print a tube segment and then I want to change it, I could just go back onto Fusion 360 and just cut out a new hole or move something to a different place. So that's what's really good about 3D printing, the airframe of the rocket. And another thing that you might notice is the parachute is on the outside here. So I ditched the whole spring loaded mechanism that was on Hopper V2 and decided to go with a really simple design which stems from the new flight computer, and you should see a picture of that on your screen, which is called REACH, and that stands for Rocket Electronic Avionics and Control Hub. And this is the first ever PCB I ever made, um, and it's pretty good. It flew really nicely, and it basically took the weight of the old flight computer, which was two breadboards stuck back to back, which made the flight computer really heavy. And definitely not lightweight. It was a really heavy unit, and it was like way too heavy. So I switched to the PCB, and it reduced the mass by quite a significant amount. I think the original avionics system was about 6 ounces, and now this is the new one is around 2. So I significantly reduced the weight of the avionics, and it just makes everything look way more professional. And recently, um, I made Reach V2, which there should be a picture on the screen there. So Reach V2 is definitely way more advanced, way more compact than Reach V1. So yeah, that is the avionics overview. The thrust vector control mount didn't really change that much. It just got a bit polished up, and um, yeah, that's the new motor mount. You can't really see it on screen here, but anyway, the launch pad got a pretty big overhaul. The launch table, the old one got completely replaced. So the other one was off level and not necessarily the best for having a rocket that requires itself to be straight up for a launch, it's not that great for that. So I put I replaced the launch table with a fully 3D printed one, which resembles the SpaceX Starship orbital launch mount. That's what I was kind of going for with this whole pad design at the start. So uh, yeah, it has the water deluge is back here. That little orange water exit. That's the water spout there, and the pipe runs back, and then the clear tube is the water pipe, and then the launch tower grew by two segments here, with of course the American flag, and then we have the pad cam here, and this thing was interesting. This has really no purpose, but it's a quick disconnect arm, so it retracts right before the rocket lifts off. And final thing with pad hardware, all inside, you can't really see it, but all inside this base area is all electronics for igniting the rocket motor on its own. So I'm not holding a controller anymore, a physical controller. I'm not pressing any buttons. The launch pad is doing everything autonomously. So that was a pretty cool upgrade for this rocket. The model here. So starting off at the bottom here with the TVC mount, I went kind of back to a blend of Hopper V1's TVC and Hopper V2's TVC. So it took the outer gimbal, which is here. You can't really see it. I'm gonna try to see if I could disable this airframe here. Okay, there we go. So you could kind of see I took the motor mount tube from Hopper V1, and I took the outer gimbal from Hopper V2, and and then I took the inner gimbal and I modified it from Hopper V1 to fit for Hopper V3. So I kind of just polished it up and made it look a bit better. So it's technically majority V1 motor mount, but um, it's just a blend, and then it made version 5 of the motor mount. So Hopper V1's motor mount was version 3, Hopper V2's motor mount was version 4, and then Hopper V3's motor mount, or Gen 3's motor mount, or is V5. And then the next rocket after this one, Gen 3 V2, uses a completely different motor mount, version 6. So here we have a bulkhead. So this basically prevents any kind of rogue exhaust or anything um, from the motor to get up into the flight computer and battery section, which this actually almost worked or almost helped out. During the flight, the motor aft cap, I have to plug the motors myself because they don't come plugged. They're SD's D12 zeros, so I have to plug them myself. So sometimes that plug might fail, so it might send hot exhaust, explosive exhaust up from the tube here into the up here. So I don't want it to hit the batteries or reach the flight computer. So we have this bulkhead here that prevents that. And in this little section between the bulkhead and the flight computer is where the batteries hang out. Okay, so like I said before, I got the airframe to come back here. So yes, this is the cutout for the motor mount here. So that's the bulkhead, and then this is the TVC section. Okay, so moving up, we have the avionics section. So this is the tube that houses the flight computer. So I'm going to disable this so you could see in. So this is the bottom ring that holds the flight computer. And then up there there it is, the top ring. So I don't think I did a good job. Actually, never mind. I think this is okay. There might be some little inaccuracies with this model, but um, yeah, so that's where the upper flight computer sits. Or not really the upper flight computer, the upper portion of the flight computer gets mounted up there, and then the lower portion gets mounted down here. Um, so the flight computer avion or the housing has all these cutouts. So this front cutout is to access the power switch and the reset button. The reset button is on the Arduino, and the power switch, if I don't have the flight computer modeled, but the power switch would be like somewhere in this region. So I would also use these cutouts here. These little boxes is for screw access or screwdriver access to the screw terminals on the flight computer. Um, and then these guys here is where the batteries, so the wires would go out and then plug in to the computer right here. And then on this side, same thing here, we got screwdriver access to the screw terminals, and then here is where the pyro channel outputs would be. So that's if you see those two yellow wires on the side of the rocket, those are the pyro outputs. That's what heated up the wire to cut the rubber band and deploy the parachute. So moving up, we had this thing which I don't really like how it looks with this, but I kind of had to do it. Since the parachute was strapped onto the outside of the rocket, I didn't want it to be aerodynamically unstable or have too much drag on one side. So I called this the parachute umbrella. So it basically deflects the air over the parachute. So it made the rocket look pretty ugly, and I despise it. It does not look great, and it didn't really do anything anyway. So moving up is the nose cone. So the nose cone had to have these wacky holes in it to support the coding wire, or the wire that ran from my laptop to the flight computer. The plug for the Arduino to upload code to it was facing the top. So for me to upload code to it and access it, the wire would have to run from my laptop to the top of the Arduino. Now, if the flight computer is situated inside the rocket, if it's situated in here, I can't necessarily gain access to that. So I would have to plug in the flight computer and then run it through the nose cone. It was really, really like a very big pain. But now with Reach V2, I have the Teensy 4.0, which is I switched. I'll make a video on the Reach flight computers pretty soon, but the I switched from an Arduino to a Teensy 4.0, so its coding port is, or I should say the USB port, is flipped horizontally. So I don't need to have it coming in from the top anymore. So yeah, it was pretty ugly, and I thought this rocket was going to eliminate all hardware issues, but it had a lot of hardware issues. So that's it for Hopper Gen 3's CAD model. See here the water system activated, which was really nice. So that kept the pad clean after the rocket lifts off. So here we have there goes the QD motor here. The launch clamps that were in there um, got pretty toasty, so um, I had to replace those, and I installed the system. And there should be a video on the screen right now um, that retracts. It uses an Adafruit BMP280 and senses the temperature inside this ring here, and if it exceeds a certain amount of degrees above ambient air temperature, it will pull back the clamps. So I'm still trying to refine that system, but right now I'm trying to make sure that these clamps don't get fried after every launch. Um, so yeah, so we have a successful ignition here. We have liftoff. So you could tell this rocket is basically springs right off the pad. I couldn't even pause it in time. So yeah, so this thing gets off the pad really fast because of its very lightweight nature. So it was able to spring right off the pad. Definitely, this rocket was expected to go around 90 to 110 feet. So that's way more than V2. V2 was around, I think it was like 20 feet, and then V1 was expected 40 feet. So Gen 3 here definitely had a huge weight decrease, which is really nice. So it pitches over here, downrange a little bit to the right and a little bit forward, and you could tell because the plume hits the flag here and hits some of this over here. So this is the wide angle camera. So you could see the pitch over more clearly here. So it gets actually around the same angle as Hopper V2 Flight 2. That it got to that same kind of angle like that the flight before this. So you could see here the motor mount is at a different angle than you could see it correcting for the rocket's orientation, which is pretty nice. So it starts to pitch back over to the left from this view. So here's the tracking. So say we have liftoff, and it corrects here, and then I don't this there was this issue with the hardware side of things where when the SD card was in, when it was writing data, I used the Arduino Nano 33 IoT for this because that's a built-in IMU. So when it would write data, it would slow the writing of the motor mount commands, so it'd be really slow. So for this flight, I kind of just I was like, screw it, doesn't matter what data I get back from this. So I just decided to jack up the gains really high so that it would counteract that slowness, but that didn't really work here. Um, so it lifted off, corrected, and then couldn't correct back in time and ended up flipping out. And the rocket called an abort here and then locked the motor mount in place, which caused the flipping. So yeah, the parachute system did its job and got the rocket down to the ground nice and soft. So yeah, this is the pad camera. So you can see the water deluge more clearly down there. Yep, there we go. So you could see the uh, clamps here. They got pretty charred, or they're not really launch clamps, they're igniter clamps. So yeah, those got pretty toasty. So yeah, the water's just pretty much getting all that stuff out. This is just the slowed down version. There goes the QD. There's ignition and then liftoff there. Yeah, so you can see some of these deposits being flushed out by the water. So the water did a pretty good job this flight, so I was impressed. This is on board. Same thing with a lot of the other flights. The onboard does not really show that much just because of how fast it's moving. Um, this is real time. You just see how fast like real time is. So yeah, I mean, it was a pretty good flight for Gen 3 V1's flight data. So as you can see, we have a bigger arc here, pretty similar to Hopper V2 test flight 2 two's data. You could see that arc and then it kind of goes out. This cuts right when it aborts. So when it aborts around here ish. Yeah, right here it aborts. So yeah, that's this. So very short, a very longer burn, I guess you could say, even though it's the same motor, just because the rocket has a longer flight time because it's gonna go was expected to go higher, which it did. Even though it aborted, it did go higher than Hopper V2. Um, yeah, so roll I properly integrated, so it looks like we reached a peak of only 10 degrees during the flight, degrees per second, I guess you could call that. So yeah, we abort here, so everything else past that point is all when it's just falling back down. Um, and yeah, this is everything together. So I mean, it's kind of better, kind of the same. The software I added the integral gain, so it's now a proportional integral controller. So the next flight, or the next one I'm going to be doing is still using the proportional integral controller. Then I'm hoping for the one after that to use a full-fledged PID controller. Um, so thank you guys for watching, and I will see you in the next video.